Hey everybody, Trey here. The podcast you're about to listen to is an AI-generated discussion focused on a transcript from my Convective Chronicles YouTube channel. Artificial intelligence is something we are constantly experimenting with at Storm Chaser Coaching, and you might be surprised to know that what you're listening to right now is an AI clone of my voice. Take care, everyone, and I hope you enjoy Convective Chronicles Reimagined.
Today, we're strapping ourselves into a really remarkable atmospheric event, the Dodge City, Kansas tornado outbreak, May 24th, 2016.
If you've ever wondered what a career highlight looks like for a storm chaser, well, this day is definitely up there. A prime example.
Absolutely. And for everyone listening, if you're curious about, the raw power of nature or just what goes into these huge events, this is a fantastic case to look at. We've got a really detailed analysis from a chaser perspective, lots of data, observations from the ground. It's almost like being there, minus the hail, maybe.
Hopefully minus the hail. So our mission today is really to dissect what came together atmospherically to let one single supercell thunderstorm churn out, something like 13 tornadoes?
Around 13, yeah. It was prolific.
Incredible. We want to understand why this storm was such a machine and what it tells us about forecasting and just the sheer force of the atmosphere.
Right, where all the pieces fit. Okay, let's dive right in. The morning of May 24th, what did things look like initially? What was the outlook?
Okay, so that morning, the Storm Prediction Center, the SPC, their day one outlook, it highlighted two main areas for severe weather potential.
Right.
One was up in northeast Colorado, southwest Nebraska way, and the other, which really became the focus, was down along the Kansas-Oklahoma border.
And within those bigger areas, they had those smaller, more focused tornado threat zones, didn't they? Like really pinpointing things.
Exactly. Both of those main regions had these small 10% tornado risk areas drawn. It sort of tells you how focused the initial thinking was. The SPC was basically saying, okay, keep a really close eye on these spots.
So what happened the night before? Did anything kind of tee things up for this? Any clues overnight?
Oh yeah, the evening of the 23rd definitely gave us a preview. We saw tornadic storms in a couple of spots.
Okay.
Near Turkey, Texas, northwest Texas, there was a pretty significant wedge tornado after dark that came from a storm merger. And then further north, near Woodward, Oklahoma, also tornadic activity around sunset. So yeah, the atmosphere was already showing its hand, you could say.
But the real game changer for the 24th, it seems, was something else that developed overnight. Right over Kansas. Not tornadoes themselves, but something left over.
That's right. That's the key. Overnight into the morning of the 24th, this big complex of elevated thunderstorms fired up across northern Kansas.
Elevated meaning their bases were off the ground.
Exactly. Probably formed north of a warm front, just kept going all night. And the really crucial result was the outflow boundary it left behind, a really well-defined one.
Okay, outflow boundary. This sounds technical, but super important, right? Why was this boundary such a big deal? What did it actually look like?
It was remarkably clear, actually. If you looked at the visible satellite pictures that morning, you could just see this distinct line of clouds stretching right across southern Kansas, like a mini cold front left over from those storms.
Okay, so ghosts of thunderstorms past, kind of hanging around. But why does that matter for making new storms, tornadic ones?
Well, what's really critical is that these boundaries become focus points for enhanced low-level wind shear.
The shear.
Yeah. Think of it like you've got the cooler air from the outflow pushing under the warmer air ahead of it. Right near the ground, that creates this zone where the wind changes speed or direction quickly with height. That's low-level shear.
And that helps storms rotate.
Precisely. It's a key ingredient for getting thunderstorms to rotate to form mesocyclones, which is the heart of a supercell and potentially a tornado. Experienced chasers often target these boundaries specifically because the tornado potential can be much higher right along them.
And the regular weather maps, the surface plots, they showed this boundary too.
Oh, absolutely. Surface maps from 5 a.m. Central onwards, they clearly showed the wind shift, maybe northerly behind it, southerly ahead, and a temperature drop, too.
Okay.
Initially, it was sitting up in central Kansas, but you could track it drifting slowly south through the morning. And interestingly, there was maybe even a hint of a second boundary, further south, across southern Kansas, northern Oklahoma.
So multiple potential focus points.
Exactly. Multiple triggers potentially on the board that morning.
Okay, so the ground level was getting set up with this boundary, this shear zone. But what about way upstairs? What was happening higher up in the atmosphere?
You got to look at the whole picture. Synoptically, at the 500 millibar level, it's roughly 18,000 feet up. The pattern was very favorable. We had a broad trough, a dip in the jet stream parked over the western U.S., and that set up a southwesterly flow across the plains. That's a pretty classic upper-level look for significant tornado days.
And it wasn't just smooth flow, right? There were subtle things within it, ripples.
Exactly. Within that broad flow, you look for these subtle perturbations, these little kinks or shortwave troughs in the height lines on the map. They might look small, but they provide localized lift.
Yeah.
And in this case, there was indeed a shortwave trough identified at 500 millibars moving right across southwest Kansas during the day. That feature helps create divergence, aloft air spreading out high up, which acts like a vacuum, helping pull air up from below.
So the upper levels were kind of helping to pull the trigger, basically.
You got it. It's like priming the pump. So you combine that upper support with the surface moisture, which we'll get to, and that outflow boundary providing the low-level shear. I mean, that's textbook. Right out of the severe weather playbook for isolated supercell tornado days.
All the pieces coming together.
They really were. And even a bit lower at 700 millibars, the analysis showed multiple little disturbances in the flow, which likely influenced exactly where and how strongly storms would initiate.
Let's dig back down to the surface then. Lee cyclogenesis. Heard that term used. What is that and how did it fit in? Sounds like something to do with mountains.
It is, yeah. Lee cyclogenesis is just the development of a low-pressure system on the lee side, the downwind side of a mountain range.
Okay.
So as that southwesterly flow we talked about moved over the Rockies in Colorado, it helped spin up a surface low-pressure area in southeastern Colorado. The mountains disrupt the flow, cause a little spin up on the other side.
And this low wasn't brand new that day, right? It had been developing.
Yeah, you could trace it back to the 23rd. It gradually organized and strengthened through the morning and into the afternoon of the 24th. Its main role here was acting like a vacuum cleaner at the surface, pulling warm, moist air from the Gulf of Mexico northward right into southwest Kansas. And the 850 millibar charts just above the surface showed that nocturnal low-level jet across the southern plains overnight, which was already doing a good job transporting that moisture northward towards the developing low.
So this low-level jet, this river of fast-moving moist air, was interacting with that outflow boundary we keep mentioning. That sounds potent.
Extremely potent. That combination, the outflow boundary acting sort of like a warm front with warmer, more humid air south of it, interacting with that strengthening low-level jet, feeding into the surface low, that created a really prime zone for storms to get going. The whole setup was focusing the energy and moisture right there.
And the moisture itself, what were the dew points like? How juicy was the air?
Oh, they were climbing, steadily increasing. We saw dew points getting into the low, even mid-70s Fahrenheit across southwest Kansas by afternoon.
Wow, 70s dew points. That's serious fuel.
That is really juicy air. Indicates a very moist, very unstable air mass right at the surface. Just a huge amount of potential energy for storms to tap into.
Now, you mentioned outflow boundaries can sometimes weaken or wash out.
Yeah.
Why is that actually sometimes a good thing if you want rotating storms?
It seems counterintuitive, but while a sharp boundary helps trigger storms, if it's too strong, with really strong winds crashing together, sometimes it forces everything into a squall line.
Okay. Less chance for isolated supercells.
Exactly. In this case, the fact that the initial boundary is perhaps weakened or washed out a bit actually led to a more uniform southerly to southeasterly wind field near Dodge City. This kind of environment allows individual supercells to develop and stay discrete, stay separate, which is often crucial for them to really get organized, rotate strongly, and produce tornadoes.
Makes sense. And the dryline, where did that fit in? Always hear about the dryline on the plains.
Another critical piece. The dryline, that boundary separating the really moist Gulf air from the much drier air coming off the high terrain to the west, was setting up right there too.
You could see it in the dew points.
Oh yeah, clear as day, sharp gradient. You had Dodge City maybe reporting 66-degree dew point, but just west in Syracuse, it was way down in the 50s, like 54. Liberal, south of Dodge, was 57. But then Gage, Oklahoma, south of Liberal, was back up near 68. So you had this bulge in the dry line right into southwest Kansas.
So everything, the boundary, the low, the moisture, the dry line was pointing right at southwest Kansas.
All the meteorological indicators were just screaming southwest Kansas for the main event that afternoon.
Sounds like a slam dunk forecast. Were there any curveballs? Any moments of doubt for chasers on the ground?
Oh, absolutely. There always are, right? The initial storm development actually fired up further north, way up along that northern outflow boundary, near Scott City, Kansas.
Oh, really?
Yeah, and that storm even produced a couple of tornadoes early on. So for a little while, there was definitely some anxiety among chasers who had committed to the southwest Kansas target. Like, uh-oh, did we pick the wrong spot? Is the show going to be up north?
A classic storm chase head fake.
Totally. A good reminder that even when everything looks perfect on the maps, the atmosphere can still surprise you.
But eventually, the action did shift back south. What finally kicked things off there?
Radar became absolutely key then. You could clearly see the Dryline signature on the Dodge City radar loop, and crucially, you could see where that outflow boundary we talked about intersected the Dryline.
The triple point idea, kinda?
Basically, yeah, or at least a very focused intersection. As our chaser source noted, that intersection is often a favorite spot for supercells to initiate. You get enhanced convergence, enhanced lift right there, and sure enough, around 5 p.m. Central, boom. Storms just exploded southwest of Dodge City, north of Liberal, right near that intersection.
Like flipping a switch.
Exactly like flipping a switch. Rapid, intense development.
And visually, what did these first storms look like as they ramped up? What were the clues they were serious?
Reports and photos from chasers showed that explosive development. The initial storm base was described as flat and broad, often a sign of really strong inflow, sucking in all that moist air.
Yeah.
And then very quickly, a wall cloud formed beneath that base, started small, got chunkier. That lowered rotating cloud is the key precursor. And you could see a distinct inflow tail, too, those low clouds streaming into the storm, all classic visual signs of a developing, rotating supercell.
All right, let's get technical for a minute with the soundings. Those weather balloons give us that vertical profile. What did they show? Was the atmosphere really as primed as it seemed?
Oh, yeah. The 12Z sounding, that's noon GMT, morning in Kansas, taken right at Dodge City, already showed a very unstable setup. Mixed layer K was over 2,500 joules per kilogram.
Which is pretty high.
Very high. That's a lot of potential energy, a lot of buoyancy for storms. But importantly, there was still a strong capping inversion, that lid of warm, dry air aloft, likely from that elevated mixed layer.
So a loaded gun scenario.
Yeah.
Lots of potential, but
Yeah.
needing a trigger to break the cap.
Exactly. A classic loaded gun sounding. The sounding from Lamont, Oklahoma, further south, looked very similar. Now, fast forward to the 19Z Dodge City sounding mid-afternoon.
Okay.
It showed the moist layer near the ground was getting even deeper, more fuel available. The cap was still hanging on, maybe weakening slightly, but still there, meaning we needed that lift from the boundary and the shortwave. But the crucial part was the wind shear. The parameters were really ramping up and becoming very favorable for tornadic supercells.
What specific shear parameters were looking good?
We were seeing high values of 0 to 1 kilometer shear that change in wind right near the ground. Also, high storm relative helicity, SRH, especially in the effective inflow layer, that measures the potential for rotation that the storm is actually ingesting. And the bulk shear, sort of the overall shear through a deeper layer, was right in that 35 to 45 sweet spot. Strong enough for supercells, but not necessarily so strong it would just create a line, although there was maybe a hint of chaotic winds higher up that suggested maybe an HP, a high precipitation supercell, could be possible.
Which can make tornadoes harder to see.
Exactly. Rain-wrapped.
Okay, but then we get to the really critical time, right when the storm's fired. What did the proximity sounding right near the storm show then?
The 22Z RAP sounding near Dodge. Right around initiation time, that showed the cap was gone, fully destabilized, and the instability was just incredible, immense, explosive potential. But maybe even more critical for the tornadoes was the very strong low-level instability.
Why is that low-level instability so key for spinning up tornadoes?
Because it allows for really efficient stretching of any spin that's already present near the ground. You've got that outflow boundary with inherent horizontal spin, that vorticity. You combine that with intense lift and stretching potential in the lowest few kilometers.
And you can quickly spin up a tornado.
That's the idea.
But
that horizontal spin gets tilted upwards by the updraft and stretched vertically, rapidly intensifying the rotation right near the ground. It's the perfect recipe, especially along that boundary.
And the Hodograph, the wind profile shape, did that look good too?
Oh, yeah. Textbook. The 22Z Hodograph showed that high effective SRH we talked about, good mid-level venting. By 2223Z, the actual Dodge City sounding, might be slightly storm contaminated but still useful, showed even stronger shear and that classic curved semicircle Hodograph shape that just screams tornadic supercells.
Lots of turning with height.
Lots of turning, especially in the low levels, indicating significant streamwise vorticity, basically, spin that's aligned with the direction the air is flowing into the storm. When a storm eats air that's already spinning the right way, making a tornado becomes much easier.
It had everything it needed.
Absolutely. Even later, the 0Z sounding near Coldwater, southeast of Dodge, still showed a highly favorable sheared and unstable environment. The threat wasn't over quickly.
So the ingredients were perfect. What did the radar actually look like as the storm unleashed hell?
It was pretty much a textbook radar evolution. Rapid development of that classic supercell shape. A really pronounced hook echo appeared quickly near Mineola, southwest of Dodge.
Classic hook.
Yep, the visual sign on radar of that strong rotation, the mesocyclone. You could practically see the vorticity from the dryline and the outflow boundary getting sucked into and wrapped around the storm's rotating updraft.
And it wasn't just one tornado, was it? This thing was cyclic.
There was this pattern where an initial tornado might form, mature, and then occlude, weaken, and dissipate off to the north side of the main updraft, while a new tornado rapidly formed just to the east or southeast.
Driven by that continuous speed of rotation.
Exactly. That strong, streamwise vorticity in the inflow just kept fueling new cycles of tornado development. It was relentless.
And the tornadoes themselves, what were they like based on eyewitness reports and damage?
The first one touched down around 6 p.m. Central, started kind of ropey, apparently, but then quickly became much more stout, much stronger looking.
Okay.
Then the storm went into that cyclic mode, sometimes with multiple funnels or tornado circulations visible at the same time. The research ended up identifying about 13 distinct tornadoes from this one supercell.
13. Incredible.
And yeah, a strong one hit the west side of Dodge City directly. Reports described it initially as multi-vortex, several smaller vortices rotating within the main circulation before it consolidated into a large, damaging wedge tornado.
Wow.
And even after passing north of Dodge, it wasn't done. More tornadoes spun up before the storm eventually started to transition, became more of a cluster, and finally weakened. It really earned the name TornadoFest that some chasers gave it.
13 tornadoes, one storm. Just wow. It really hammers home how complex and powerful these systems can be. A day people will analyze for a long time.
No doubt. It was an absolutely exceptional event. A perfect storm, literally, where all the different atmospheric factors aligned just right. And analyzing cases like this, in this kind of detail, is so crucial for understanding severe weather better and, hopefully, improving forecasts down the line.
And for everyone listening, we really hope this deep dive gave you a clearer picture of the amazing atmospheric dance that leads to these powerful storms. It's just a stunning display of natural complexity and energy.
Yeah, and it really highlights how, even with all our technology and knowledge, these storms can still throw surprises at us. There's always more to learn, which is why the research continues, and why chasers and meteorologists stay so dedicated. Maybe think about this. Even when all the signs point one way, how much uncertainty still remains in predicting the exact behavior of something so powerful?
Thanks for tuning in to Convective Conversations. If you found this episode helpful, make sure to subscribe so you never miss an episode. Want to take your skills to the next level? Join us inside the Chaser Academy. That's our in-depth training program for storm chasers who want to chase smarter and safer. Just click the link in the description to subscribe. And if you're looking for community, we've got a free space where hundreds of chasers and weather enthusiasts are sharing forecasts, asking questions, and learning together. You'll find that link in the description too. Until next time, stay safe and keep chasing.